Dear all the students of B.Tech first year, I am Dr. Ravindra Parsai, Associate Professor of Mathematics in Engineering Science Humanity Department at Chamil Devi Group of Institution Indore. I want to teach you today in this 8th lecture of unit matrix algebra, diagonalization of a matrix and the Cayley-Hamilton theorem with its application to find inverse. So first we understand what do you mean by diagonalizable matrix. So if A is a square matrix of order n, has n linearly independent eigenvectors x1, x2, x3, xn, then a matrix B can be found such that B inverse AB is a diagonal matrix where B is called the model matrix and B is designed by with the help of eigenvectors of a given square matrix. Since we have already seen in the previous lecture how we find eigenvectors, just like that we will see its application how when a square matrix is said to be a diagonalizable. Let me understand this by an example. So the question is asked by this way: verify the diagonalization of a matrix is 6 minus 2 2 minus 2 3 minus 1 2 minus 1 and 3. So our first objective is to find the eigenvectors of this square matrix. So before this we will find first the eigenvalues of the matrix. For this you have to write an characteristic equation determinant of A minus lambda equal to 0, that is 6 minus lambda minus 2 2 minus 2 3 minus lambda minus 1 2 minus 1 3 minus lambda equal to 0. So when you solve this determinant you will get 6 minus lambda 3 minus lambda whole square minus 1 minus 2 minus 2 minus 2 3 minus lambda and plus 2, then plus 2 by taking this element and their minor is minus minus plus 2 minus of 2 of 3 minus lambda equal to 0. So this gives you an cubic equation lambda cube minus 12 lambda square plus 36 lambda minus 32 equal to 0. So we have seen in the previous examples how will you find the root of this equation as. So since lambda equal to 2 satisfy the above equation, therefore lambda minus 2 is one factor of it, that is lambda square minus lambda minus 2 minus 10 lambda minus 2 16 plus 16 lambda minus 2 equal to 0, that is throughout you will take lambda minus 2 common, you will get lambda square minus 10 lambda plus 16 equal to 0. That is by factorizing this quadratic equation you will get the factors of lambda minus 2 and lambda minus 8, that is you are getting the eigenvalues 2 2 and 8. Now we will find the corresponding eigenvectors. For this we have characteristic value problem, matrix A minus lambda I over x equal to 0, that is 6 minus lambda minus 2 2 minus 2 3 minus lambda minus 1 2 minus 1 3 minus lambda x y z 0 0 0 0. Now you are putting lambda equal to 2 in the equation 1, you will get, for finding first eigenvector for lambda equal to 2 you will get the characteristic value problem is 4 minus 2 2 minus 2 1 minus 1 2 minus 1 1 x y z 0 0. Now the process is, you since the first row is divisible by 2, that's why divide by 2 as a elementary row operations, you will get 2 minus 2 minus 1 1 and minus 2 1 minus 1 and then 2 minus 1 1. Now you will make with the help of this 2 minus below elements to 0. So on applying R2 plus R1 and R3 minus R1, this gives you 2 minus 1 1 0 0 0 0 0 0 and of this. So therefore you are getting this an echelon forms. Now you can find the rank is, for this echelon form is rank 1, and while for lambda equal to 2 and number of unknowns are 3. So in such case you will find the total number of linearly independent eigenvectors are 3 minus 1 equal to 2, and we will find as follows by writing the previous metric equation into algebraic form: 2x minus y plus z equal to 0, that is by taking y equal to k1 and z equal to k2, so you will get x from this. So on putting one equation, you will get x equal to k1 minus k2 upon 2, that is for lambda equal to 2 you are having the eigenvector k1 minus k2 upon 2, k1 k2. So now you separate as you write by sum of two matrix, one is x1, another is x2. That is, now you will find the eigenvector corresponding to lambda equal to 8 by putting in the first one. You will get minus 2 minus 2 2, minus 2 minus 5 minus 1, 2 minus 1 minus 5, x y z equal to 0. Now by this same process you make this position element to 0, so this gives r2 minus r1, r3 plus r1. You will get here minus 2 minus 2 2, 0 minus 3 minus 3, and 0 minus 3 minus 3, x y z 0 0. Now with the help of this element you make below element 0 on applying r3 minus r2. So you will get this echelon form. Therefore the rank of the coefficient metric is 2, and for lambda equal to 8 and number of unknowns are 3, and the number of linear independent eigenvectors are the minus 2 equal to 1. So that is minus 2 minus 2y plus 2z equal to 0, which you find by simplifying the previous metric equation into algebraic forms. And the second one is minus 3y minus 3z equal to 0, that is y plus z equal to 0, that is y equal to minus z. Here z equal to k3 you will assume, where k3 is any real values, so you will get y. When you get x and y, when you get z and y, you will put in equation number 1, you will get x equal to 2k on putting this value into this. So therefore the eigenvectors corresponding to lambda equal to 8 is x y z 2k3 minus k3 of k3. Now we will define an model matrix by using this concept. Here you are having three eigenvectors, you will take x1 x2 and x3. So by taking k1 k2 and k3 equal to 1, so from the previous one you will get first eigenvector is 1 by 2 1 0, second eigenvector minus 1 by 2 0 1, third eigenvectors when you put k3 equal to 1 2 minus 1 and 1. So in this way you will design a model matrix from the eigenvectors. Now our objective is to find its inverse. So for this we use adjoint method. So you everybody know, well acquainted with how to find adjoint of a matrix. Just like that we proceed now by finding first row the cofactor of all elements, then finding the cofactor of second row, then finding the second cofactor, third row cofactors. So let me start with this. First row, first element, you will find the cofactor is minus 1 raised to 1 plus 1. If the position is first row, first column, you will take 1 plus 1, and the minor is 1. Therefore you multiply by this, you will get 1. Then you take first row, second column elements cofactor, you will add minus 1 raised to 1 plus 2, and the minor is 1. So on solving this, minus 1 ki power 3 is minus 1. So that's why you will get the cofactor of second column first row element is minus 1. Then similarly you will find first row third column cofactor is 1. Then similarly you go for second row first column element, and the minor is minus 5 by 2. That's why the answer is minus minus plus 5 by 2. And then C2 you will get minus 1 is to 2 plus 2 1 by 2, that is 1 by 2. Then the cofactor of second element third column of the previous matrix is minus 1 is to 2 plus 3 5 minus, so that's why minus 1 by 2. Now you come to the third row cofactor, so 3 comma 1, and this 1 by 2 second element of third row is minus plus 5 by 2, and the third row third column element cofactor is 1 by 2. With the help of this cofactor of all the elements, you are finding the adjoint of the matrix B by writing in transpose form. So 1 minus 1 first column 1, then second column is obtained by writing these elements cofactors on the column forms. Similarly, third column you will get. And now before finding the inverse of the metric by adjoint method, you have to find the determinant of this method. When you find the determinant of this method, you will get the value is 3. Now on this basis you are able to find the B inverse by adjoint method as adjoint of B upon determinant of B. So just divide all elements of the adjoint of matrix by the value of determinant of B. You will get this metric 1 by 3, 5 by 6, 1 by 6, minus 1 by 3, 1 by 6, 5 by 6, 1 by 3, minus 1 by 6, and 1 by 6. Hence you will find the product of these three matrices. So B inverse AB. So for this you know that first writing this matrix, then you write this matrix, then you write this matrix. So by multiplying at a time any two matrix out of these three matrix, and whatever will be the answer you will get, you multiply with third matrix, you will get the matrix is product is 2 0 0 0 2 0 0 0 8. That is, this is a diagonal matrix in which diagonals are 2 2 8. Since the diagonal elements of this matrix is just nothing but the eigenvalues of the given matrix, hence we show that, or we can say that the given matrix is become a diagonalizable matrix. So this is all about a diagonalization of a matrix. Now we come to the one of the famous scientists who have been worked on a square matrix and the quadratic equation, and they have given you a very important statement that is called a Cayley-Hamilton theorem. Is as follows: every square matrix satisfies its own quadratic equation. For this, let we see the verification. So we know that if A is a square matrix of order n, then the quadratic equation of the matrix is determinant of A minus lambda equal to 0. That is, it is a polynomial of degree n. That is, we assume, we find here, we write in general form as follows: minus 1 is to n, a0 lambda ki power n, a1 lambda ki power n minus 1, a2 lambda ki power n minus 2, dot n equal to 0. So then, to prove this theorem, if lambda is replaced by a, then the above equation is satisfied. That is, we have to obtain, if you are able to find this equation, then this shows that Cayley-Hamilton theorem is self-proved, self-verified. So actually it is a self-proved techniques, but we are going to verify it analytically. So for this, very special approaches adopt for verification of this result is: first we assume the by matrix B as a adjoint of this matrix A minus lambda A. Then we know that it is a polynomial. That's why it is adjoint when you take the degree becomes less than 1. Whenever you take adjoint of a matrix, then the polynomial you are getting always a degree of n minus 1. So that's why it is a polynomial of n minus 1 degree in lambda. Lambda is a scalar. That's why we assume that this is to be b0 lambda ki power n minus 1, b1 lambda ki power n minus 2, b2 lambda ki power n minus 3, dot up to bn. Now the next step is just multiply this equation 2 by a minus lambda a on the both side. So now you are doing this type of manipulation in the equation number 2 as multiply equation number 2 by a minus lambda a. This gives to you this. Now we are going to substitute on the both side the corresponding values. So that is a minus lambda equal to b equal to determinant of a minus lambda into I. One more important property of adjoint of a matrix we are using, you are using at 12th class level number of times, as a into adjoint of a is always equal to determinant of a into unit matrix. So this one of the most important property of an adjoint of a matrix is useful here. And now you are going to substitute the respective values here. So a minus lambda as it is, on putting the value of b this side and on putting the value of this quadratic portion in the right hand side. That is, this is the left side of this equation and this is the right hand side of the above equation. Now the next step is to just on simplify this, multiply this, and then on equating the coefficient of like powers of lambda on the both side. You will get first by taking the constant term coefficient, you will get this value minus b0 of I minus 1 raised to n of a0 into I. Next coefficient you will equate to 0, equate to right hand side, you will get a b0 minus b1 of I in left side, while on the right hand side you will get minus 1 raised to n of a1. That is by equating the coefficient of lambda raised to n minus 1, then equate to 0, not equate to 0, you equate the coefficient next power of x lambda as lambda raised to n minus 2. You will get this, and so on up to in the last step you equate on the both side the coefficient of constant terms. This you will get. Now after one manipulation by pre-multiplying this equation by, because I want to obtain a expression of having the matrix capital A raised to n minus 1, a raised to n minus 2, and dot up to a. So that's why we multiply, pre-multiplying all the above these equation by these factors, a raised to n by first one, a raised to n minus 1 the second one, third one, and so on, the second last one a by a, and the last one by unit matrix I, and then adding up all these expressions. So on adding up all these expressions, sometimes are to be cancelled. You will get by taking this common, this term you are getting. So what is this? It is nothing but this shows the Cayley-Hamilton theorems. And now our objective is to find, how will you find a square of a inverse of a non-singular matrix by using Cayley-Hamilton theorems. So with the help of this Cayley-Hamilton theorem, easy to find inverse of a matrix. You can say that just multiply this equation by a raised to minus 1. So by multiplying this equation by a raised to minus 1, and by writing only a raised to minus 1 term left side and all rest terms you shift it on the right hand side, you will get the value of a inverse by Cayley-Hamilton theorems. Let me see an example on this topic, then our this session is over. So verify Cayley-Hamilton theorem. Question is asked by this way: verify Cayley-Hamilton theorem and to find a inverse and also find a raised to 8. We are having in this question two applications, one is a inverse, another is a raised to 8. So if matrix is this, okay, there is no problems. First of all, you write the eigenvalue equation or a character equation of the matrix. Our eigenvalue is defined by this character equation. So that is by determinant 1 minus lambda, 2 minus 1 minus lambda. So that is minus 1 over whole square minus 4, that is lambda square equal to lambda square minus 5 equal to 0. Now to verify the Cayley-Hamilton theorem or to prove Cayley-Hamilton theorem, we have to prove that if lambda is replaced by a, then the above equation is satisfied, that is a square minus 5i equal to 0 matrix. So for this you have to find a inverse. So you know that by matrix method, how will you find a square? Just for finding a square you have to write a into a. So multiply these two matrices each other. So by taking first row and first multiply the corresponding element of first column of the second matrix, you will get first row. So 1 into 1, then 1, then 2 to the 4, 1 plus 4, then this is your first element. Second element you will get by multiply by second column. So 1 is to 2, 2 minus of 2, so this position is 0. Then similarly you will get second row of this matrix, multiplying the second row of this matrix 1 by 1. So 2 to the 2 1 ja 1 2, then minus 1 minus 2, that is 2 minus 2, and then 2 2 ja 4, and minus 1 is plus 1. So 4 plus 1, that is 5, and this is to be 0. So you will get a square equal to 0. Now you are putting in the LHS of 1, this value here, a square minus 5y, let us find out. So a square is 500 and I is 5 into 100. That's why now multiply by 5 and then subtracting this, you will get 0 matrix. It means you will get right hand side. That is, the Cayley-Hamilton theorem is verified. Hence proved Cayley-Hamilton theorem. Now we see its application for this. Multiply equation 1 by inverse on the both side. You get a raised to minus 1 equal to 1 by 5 times of a, that is 1 by 5. What do you mean by a? Just putting this, you will get this first answer. Now you will find the next answer. To find a raised to 8, for this we have from equation 1 a square equal to 5i. Now you write a raised to 4. A raised to 4 is a square into a square, so that is multiplying 25, 5 into 5, 25, I into I, यूनिट मैट्रिक्स, वन यूनिट मैट्रिक्स अनदर यूनिट मैट्रिक्स का मल्टीप्लिकेशन करेंगे, you will get unit matrix itself. So that's why you want to do this. Now repeated application of this method, that is a raised to 8 can be written as by law of index, a raised to 4 into a raised to 4, you will get 25, 625. So then multiply by I into I is I, so that is 625 multiply by unit matrix, that is you are getting the value of this matrix a raised to 8 is 625, 0, 0, 0. Thanks a lot.